And for our moment force, so we simply have to make use of the equation that is W squared all over 12. So this is for a uniform loading, so which means that at the beginning of the member and at the end of the member. At the beginning of the member, so that is WL squared all over 12, and at the end of the member, that is negative WL squared all over 12. And if we try to substitute the value, our our W here is equivalent to, which is now, so that is equal to 0.2. So times 240 squared all over 12, and we get a value of 960 kips inch. So which means that a moment force at the beginning is 960 kips inch, and moment force at the end, which has negative 960 kips inch. So therefore, if we're going to have now the member fixed end forces for member 2, we write that in matrix form. We have now the value negative 18, 24, 960, negative 18, 24, and negative 960. And therefore, our member end forces in the local coordinate system for member 2, we simply have to substitute our equation k times u plus q sub f4. That is q sub 2, which is for member 2, is equal to k sub 2, u sub 2 plus q sub f sub 2. So if you try to substitute that one and you try to simplify, you have now the value for our member end forces in the local coordinate system. So we have to take note that we have to write the unit for each of the numerical value for our axial force, our shear forces, and moment forces at the beginning and at the end of the member, since they have different units. For the axial and shear forces, they have the same, but for the moment force, of course, it would have a different unit from the rest. Now we move on to coordinate transformation. So since not all members on the plane frame are directed in the same direction, so which means that the plane frames usually contain members that are directed or oriented in various directions. So therefore, it is necessary to transform the stiffness relations of the members of a plane frame from their local coordinate system to the global coordinate system before they can be combined to establish the stiffness relation for the entire frame. So again, we're going to make use our Q, which is member end forces in the local coordinate system, and our F to represent our member end forces in the global coordinate system. So which means that if we are going to transform our our member end forces in the global coordinate system to member end forces in the local coordinate system, so which means we have this equation. So this is transforming global member end forces to local member end forces. So that is now Q is equal to T times F. And of course, for every member, there will be 6 member end forces in the local coordinate system, and there will be 6 member end forces in the global coordinate system. So it is being written in this manner. And this one is our T, our transformation matrix, and that is equivalent to this equation. So we have the presence again of cosine theta and sine theta. So to identify the value for our cosine theta and sine theta, same formula that you will be using as you identify that one in our plane truss. So you simply, after you have identified the value for cosine theta and sine theta, you simply have to substitute to this equation, then substitute to our equation here, then we can compute now for our member end forces as we transform that one from global to local coordinate system. And if we're going to transform our member end displacement from global to local coordinate system, so we can have this equation. U is equal to transformation matrix T times V. And of course, for every member, there will be 6 member and displacement in the local coordinate system and 6 member and displacement rather in the global coordinate system. Of course, our U is the end forces and displacement in the local coordinate system. Our V is the end displacement in the global coordinate system. So for this one, if we're going to have for every member, so which means that will be U. For example, that will be U sub 1, U sub 2, U sub 3, U sub 4, U sub 5, up to U sub 6. And this is equal to our transformation matrix. So this formula for our transformation times our V sub 1, V sub 2, V sub 3, V sub 4, V sub 5, V sub 6. You simply have to substitute that one. Then you simplify, you can have now the value for our end displacement in the local coordinate system as we transpose that from global to local. If that is member 1, you know this is member 1. If that is member 2, that will be member 2, and so on and so forth. So that is how we're going to transform a global coordinate system to local coordinate system. Now, if we're going to transform local coordinate system to global coordinate system, so which means transformation of local member and forces denoted by Q to global member and forces denoted by F. So this is now the formula. F is equal to T transpose times Q, and this will be our equation. So we simply have to identify again our transformation matrix and transpose that one. So meaning to say, when you transpose, the formula for our transformation matrix was the formula that was presented a while ago. However, you have to transpose that one, which means that the vertical, the column, the elements on the column will now be the elements on the horizontal for our transpose transformation matrix. Then you substitute that one. So then multiply to our local coordinate system. Then you can have now your F, which is the global coordinate system, and this is per member as well. So there will be 6, of course, for every member. If that is member 1, so this will be F sub 1 is equal to, we mean to say that is for member 1. If that is member 2, so which means that you're going to have here F sub 2 to represent member 2, and member 3, member 4, and so on. Now, if we're going to have a transformation of local member and displacement denoted by U to global member and displacement denoted by V. So this will be the equation. So you have V is equal to T transpose times U. Again, you have to identify your transformation matrix, then you transpose that one. And for every member, there will be 6 and displacement in the global coordinate system and 6 member and forces in the global coordinate system. So which means that if that is in member 1, for example, you have V sub 1 is equal to, you have here V sub 1, V sub 2, V sub 3, V sub 4, V sub 5, V sub 6. And this will be equivalent to transpose of transformation matrix times, you have U sub 1, U sub 2, U sub 3, U sub 4, U sub 5, and U sub 6. So you have now the equivalent value, and you simplify that one, you have now the value for your global member and displacement as you transpose your local member and displacement to the global member and displacement. Now for the example, the displaced position of member 2 of the frame is given in the figure. Calculate the end displacement and end forces for this member in the global coordinate system. Is the member in equilibrium under the global end forces? So for this one, we are going to make use of the, this is actually the figure for our given problem, and this is the figure. This problem was in the previous problem, which is problem 6.2, and we're able now to identify our member end displacement in the local coordinate system based on our solution. So this is now the value for our member end forces in the local coordinate system, as we computed that one in the previous problem. And similarly, this is also the value for our member end forces in the local coordinate system Qs of 2. Now we are going to compute for member end forces and member end displacement in the global coordinate system. So which means that we have to identify the value for our cosine theta and sine theta for member 2. So which means that using the equations that we have learned in plane truss, so we apply that one. So for this one, we have now a value of 0.8 for cosine theta, and sine theta is negative 0.6, which substitute this cosine theta and sine theta to our transformation formula. So for member 2, this is now the value for our transformation formula. So therefore, we can transpose, since we are given with our local coordinate member and displacement in the local coordinate system, so we can transpose that one. So which means that our member and displacement in the global coordinate system is given by this. So this is now the, as we try to substitute, this is now the equivalent value for our member and displacement in the global coordinate system. Now we are going to compute for our member and forces in the global coordinate system. So using our transformation matrix transpose. So we have here, multiply that one to our member and forces in the local coordinate system Qs of 2. So if you try to simplify that one, you get the value now for your member and forces in the global coordinate system, which is f sub 2. So this is now the corresponding value for our f sub 2. And you're going to have here, these are 8 numbers. You have to take note that this one, this member and this moment forces was just converted from inches to feet, similar to this, from inches to feet. Those are moment forces that was converted from kips inch to kips feet. So that is the main reason why we have 8 values. Actually, there are only 6 values for our member and forces in the global coordinate system, since we only have axial force, shear forces, and moment forces at the beginning and at the end of the member. For the member stiffness relations in the global coordinate system, so which means that we're trying to establish the relationship of our stiffness coefficient, our global member and forces, and our member fixed end forces. So if we're going to establish actually the relationship to that, we can have this equation. So member and forces in the global coordinate system is equal to this equation, transpose of the transformation matrix times Q, or that can be equivalent to transpose of the transformation matrix times K times U plus T raised to T Qs of F. Now for this can also be written in this manner, wherein we have our transpose of the transformation matrix times small letter K times transpose times our end displacement in the global plus transpose of transformation matrix times our Qs of F. Or we can simply have our equation for the global member and forces equal to capital letter K, which is our stiffness coefficient in the global coordinate system, times our member and displacement in the global coordinate system plus f of F. So for our K and our f of F actually can be written into this equation, wherein we have transpose of transformation matrix times our stiffness coefficient in the local coordinate systems times our transformation matrix, and our f sub F, that is equivalent to the transpose of transformation matrix times our member fixed end forces.